welcome. Today we are going to study a second order linear ODE. We would actually derive the suitable ODE for which we can write down one stochastic representation. We would start with considering some PDE which we have already seen before, for which we have already obtained stochastic representation. When I say stochastic representation, I mean solution written in terms of conditional expectation of some functional of Brownian motion. Okay, so here we start with this Cauchy problem. Okay, so this is Cauchy problem what we have seen in earlier class when we studied the Feynman-Kacâ formula. Okay, Feynman-Kacâ theorem. So there we had one more extra term, G term, which is absent here. So this is a special case of the class what we have already studied. So consider such initial value problem. So remember that we have retained this initial value problem as a corollary of the Feynman-Kacâ theorem, because Feynman-Kacâ theorem was presented as a terminal value problem. Correct? So this we call the corollary 10 in the last lecture. Okay. So here u is a function of t and x, k is a function of x, okay, and f is the initial data. This is also a function of x. We assume that k and f are continuous, and what we do is that let u be the solution of the above problem such that for some alpha positive the following are true. Okay, so here we would assume appropriate condition on f etc. Okay, so that this following conditions are true. First is that integration 0 to infinity e to the minus alpha t mod of utx dt, okay, is finite for each x, and limit t tends to infinity e to the minus alpha t utx goes to 0. This is equal to 0. We know that e to the power minus alpha t goes to 0 as t tends to infinity, but here by stating that what we are saying is that the growth of u would be dominated by the decay by this exponential function. And another thing is that we also assume that u is such that the Laplacian of the integration of this product of the function is the same as integration of the Laplacian of these product functions. Okay, so that is these are the three conditions we assume that u satisfies these conditions. Okay, I mean this would be true for some assumptions of k and f which we are not specifying now. We are just saying that let u be a solution of this Cauchy problem such that these three conditions are true. Okay. So this slide is basically derivation of an appropriate second order ODE for which we are going to write down the stochastic representation. So to this end, for derivation we would require this 1, 2, 3 properties. Okay, under these three conditions only we can do that. So we are assuming these three conditions here. Okay, so we assume, define this function z alpha for a fixed given alpha. Okay, as alpha I have mentioned here. So for this alpha, z alpha is a function of x. It is not a function of t. So we integrate this e to the minus alpha t utx with respect to t, and then this right hand side is independent of t. Okay, so we get a function of x here. So this is basically Laplace transformation, correct? Laplace transformation of this function for each x, correct? So this satisfies. Now we consider half times Laplacian of z alpha x, and already those three conditions we are going to use now at this stage. We can take this Laplacian inside this integration. So left hand side is equal to integration 0 to infinity e to the minus alpha t half times Laplacian u dt. This is equal to, now we are going to use the fact that u solves the Cauchy problem. So Laplacian of u is equal to del u del t plus k u. So half times Laplacian of u is equal to del u del t plus k times u. So that is the fact we are going to use here. We are not writing x dependence at each and every stage. but this should be understood. So integration 0 to infinity e to the power minus alpha t del u del t plus k of x times u of t comma x, okay, dt. So this we again what we do is here we add and subtract some factor for simplification. So we subtract this factor alpha times e to the minus alpha t times u, and here we add alpha times e to the minus alpha t u, okay. So e to the minus alpha t del u del t, this term is here, and then we have this subtraction minus alpha times e to the minus alpha t u. So this together we combine to write down, say, t derivative of e to the minus alpha t u t x, correct. T derivative of e to the minus alpha t u t x would be minus e to the minus alpha t del u del t plus minus alpha, because the derivative of this minus alpha times e to the minus alpha t and u, okay. And then this part already k was there, k plus alpha is there, so that also we keep, okay. So now we perform the integration. For performing integration with this t, we can take integration t here inside, because k is function of x, it is not a function of t. So we can take k outside, k of x plus alpha, okay, and integration 0 to t infinity e to the power minus alpha t u t x dt, okay. So at this stage I am writing that expression of t and x explicitly, and here as I have explained that, okay, this integration when we perform, since this partial t derivative of this thing, and then integration with this t would give me just this antiderivative e to the minus alpha t u t x, but then at should be evaluated at t is equal to infinity, and then subtract with t is equal to 0, okay. So these cases, so that means that, okay, we need to take the limit t tends to infinity of e to the minus alpha t u t x, okay. But that we have already assumed here in point 2 that this is 0, okay. So we can write down 0 here, and this when we put t is equal to 0, we would get e to the 0, that is 1. So we would get u of 0 comma x. So we get kx plus alpha times this whole thing. This is j alpha x as defined, so we write down that as z alpha x, okay. This whole thing is z alpha x. So we have obtained one equation of z alpha x here. So here we write down, more clean manner. So here u0x is basically the initial condition, that is f is already given, so minus f of x, okay, and then k of x plus alpha z alpha x. So it is now basically, since x is from Rd, so this is actually a PD, okay. So Laplacian z alpha is equal to some particular function f, okay, minus f, and then some another function here. Here it is not any arbitrary function, because k is non-negative function, but alpha is a positive number. So k is so k plus alpha would be strictly positive, so some strictly positive function. So here we can also have f plus k continuous, etc. As we have assumed earlier, we can just keep those things, okay. So this type of differential equation, this z alpha would satisfy. Thankfully, we have a stochastic representation of u, because u is the solution of the Cauchy problem, and for that, under some conditions on f, we have established that, okay, it can be written as conditional expectation of some function of Brownian motion. So that we can actually use here to write down z alpha also in terms of some conditional expectation, correct. So that is the idea. So therefore the solution to this half times Laplacian z is equal to alpha plus k of x times z minus f could be represented as 0 to infinity integration of e to the minus alpha t, and then u is replaced by this, okay. So exactly that what appears in the Feynman-Cake formula. Expectation of f of wt e to the power of minus 0 t k w s ds given w0 is equal to x. The whole thing is a function of t, but you integrate it to t, you get just a function of x, okay. So this whole thing we can also rewrite in the following manner. So this is just if satisfies certain condition, then you can interchange the integration and the expectation, okay. So because this part is bounded by 1, okay, so only this part. So here this will be under some condition f, you can do that, and note that the coefficient of z here is strictly positive. Okay. So whenever you would have similar kind of equation, okay, that half times Laplacian z time, and here you have strictly positive coefficient z minus f, you have a hope that you would be able to write down the solution in terms of this. Okay. But till now this is not completely rigorous way, so we are going to state this as a theorem, and under what condition, I mean, we can perform everything as we wish. So here this much is actually showing us that derivation of this equation for which you can hope to get this type of representation. Okay. So note that the coefficient, okay, so this is made precise below. So this is the theorem by Kacâ in 1951, that let f and k be piecewise continuous functions. Okay. They don't need to be continuous, but at least piecewise continuous function. F may be positive or negative, but k is non-negative. Okay. And for on f we have this particular condition, that mod of f of x plus y into e to the power minus mod y square root of 2 alpha dy, this is finite for all x in R. Okay. This condition looks a little different than the condition, the initial conditions what we have seen, for example, for Fermat formula. Okay. So there we require that e to the power minus a x square mod of f of x dx, I mean, that should be finite, where for some positive a. But here it looks a little different. I mean, that would be explained in successive slides. Why do we need a little different, and what is the use of those? Okay, so for some fixed constant alpha positive, okay, so this is finite, fixed alpha positive. Then for this alpha whatever it is, okay, so then zx as in 2, okay, in 2 we have already defined this zx, okay, so this is the expression, okay. So here we have this particular alpha also. So whatever alpha you would get for which this is finite, you take that alpha there, and then you would get expression of z from here, okay, and that z satisfies the following differential equation. Here we note that we are considering only one dimensional case. So earlier f is function from the space, so space was always considered as d-dimensional Euclidean space, but here we are just considering only one dimensional case for the statement and the proof of the theorem. Okay. So here, since it is one dimensional, so Laplacian is just the second derivative of z. Okay. So alpha plus k times z is equal to half times double derivative of z plus f. Okay. So this would be satisfied if not on the full real line, but at least on the points where f and k, I mean, either of them are, I mean, both of them are continuous. Okay. So here I am writing that I mean, set of points of discontinuity of function f is written by d subscript f. So d subscript k is a set of all points of discontinuity of the function k. Since f and k are not continuous functions, piecewise continuous, there could be point of discontinuities. What is the meaning of piecewise continuous? That means that you would be able to get I mean, points, okay, and basically you would be able to get subintervals on the real lines, okay, partitions, and then inside the subintervals it would be continuous. Okay, so on that this equation would be satisfied. Now a special case, k and f both are continuous, then this df and dk would be empty set. So then this equation will be satisfied on the whole R. So this is a little general version of that thing. Okay, so we start the proof here. Okay, before proof we clarify that what are we going to do. We are not here trying to prove that this equation has, I mean, what we are trying to do here is that the z what is defined here is going to satisfy this equation. Okay. Okay, so and also zx is piecewise C2. Okay, so like I mean, otherwise I cannot talk about that, the second order derivative, and that is here. So at least some those points of continuity. Okay, so this is the thing. So today we are going to see that the z, what is defined earlier, which is conditional expectation of integration of this thing, is going to satisfy this equation. Okay. So for that, we first, for a piecewise continuous function g satisfying this condition, we can write down the resultant function. So this mod of g of x plus y e to the minus mod y square root of, here it is typo, 2 times alpha dy is finite. Under this condition, we can define this g alpha g. So let us see, I mean, what is the, I mean, why do we need this condition? So here g alpha g is defined as expectation of integration e to the minus alpha t g w t dt. So it looks like, like Laplace transformation of this function of t, for every omega. So here what we do, we find out this conditional expectation, because wt is a normal random variable with mean 0 and variance t. So we can find out this expectation by multiplying this integration by the probability density function and then integrate with respect to y minus infinity. So that we do here, e to the minus alpha t g of y plus x. So this x is as before, but y is the wt value. So y and 1 over square root 2 pi e to the minus y square by 2t, because t is the variance, and dt dy. Here, since we have this condition with us, so what we are going to do is that we are going to compute integration with respect to t variable. G does not depend on t, g comes outside, and then this is e to the minus alpha t of 1 over square root 2 pi e to the minus y square by 2t. So this is Laplace transformation of this PDF function. And for that we know the expression. So one can also use some integral calculator. So that integration turns out to be 1 over square root 2 alpha times e to the power of minus mod y square root of 2 alpha. So here you have square root 2 pi t. So this function is function of t, this also depends on t, this also depends on t. All these three things together, you integrate from 0 to infinity, you are going to get this. If you want to perform this integration by yourself, you would see that that error function, I mean the actually complementary error function do appear there, and then the behavior of the complementary error function as extends to infinity or minus infinity, that those things are used to get this expression. So now this expression is independent of t, there is no t here. Now here we see that above things appear here. So g of y plus x e to the power of minus mod y, this square root of 2 alpha dy we obtain here. So that is the reason that we have to assume this. We have to assume this, I mean, otherwise we are not sure that whether this would exist. Now since this whole thing is in L1, this integrand, so we can find out this integration, and we write down this here this way, and mod of y minus x we can write down, because just change of variable formula. Here instead of y plus x we did just write y here, so that we get minus of mod of y minus x. And that now here y from minus infinity to x, there y is smaller than x, so y minus x is negative. So instead of minus mod y minus x, we just write y minus x for minus infinity to x range, and the complementary range x to infinity, on the other hand, x minus y becomes negative, so we write down e to the power of x minus y square root of 2 alpha. Simple. So this thing is written as sum of these two integrals. So here we have understood quite nicely that what is my g alpha g x. But why are we using this function g alpha g? That will be clear in the subsequent slides. Here at least what we have obtained, that g alpha x as defined in this manner is the integral of some functions here. So this is a measurable function. And then since we are integrating this with respect to y is from here minus to x, and here, so we can obtain that that this is absolutely continuous in x, because this is integration of a measurable function here. So what we are going to get that this whole integral is a absolutely continuous. This is L1 function also, correct? Not only measure, it's a L1 function. We are integrating, so we are going to get absolutely continuous function in x, and we know that absolutely continuous function is almost everywhere differentiable. So g alpha g, this function is differentiable in x almost everywhere sense. Since it is differentiable, so we differentiate, okay, with respect to x, and then so this is Leibniz rule, correct, for integration when you have this, the function is given as integral, and also the x variable also appears inside. So you do that. So here we don't know that whether g is continuous or what, okay. However, if it is continuous, then we know that, okay, its derivative. So one part will be g of x times e to the power of x minus x, that is e to the 0, and then plus then this integral, but here you do the derivative with respect to x, correct? But even if it is not continuous, even if g is not continuous, we can observe that this coefficient appears here and here, and when you put y is equal to x, so both these factors are same, like 1. And here x is in the lower limit, here x is in the upper limit, so both should actually cancel each other. So we don't need to worry about the derivative with respect to these variables. We just need to worry about the inside variable, okay, because those would cancel, okay. From here, whatever you are going to get, you get the negative sign there, okay. So when you do that, inside you take the derivative here, so x is multiplied with minus square root of 2 alpha here, it is multiplied with square root of 2 alpha, and here also you have square root of 2 alpha in the denominator, so that would go. So you have just you are going to have only integration x to infinity e to the power x minus y square root of 2 alpha gy dy minus integration minus infinity to x e to the power y minus x square root of 2 alpha gy dy. This is true for all x in R. Now, next step here, we are going to see that here what is the second derivative of the resulting function, okay. So for that, what we do is that with respect to x, if we take derivative, then this is g of x and e to the power x, and this is 0, okay, e to the power 0 is 1, and here this side you are going to get here e to the power of y is equal to x is e to the 0, that is 1, and here also g of x here. However, here we have a minus sign, we have a negative sign. Since it is a negative sign, so they would not cancel, because here we have minus gx, here we are going to get minus gx, okay, so minus 2 gx, okay. So that is the reason, since they do not cancel, so to get this we really need that g to be continuous at that point x, otherwise we are not going to get this thing, okay. So only so the point x which is not a point of discontinuity, for that we are going to get this factor, and then in the derivative with respect to x inside, that part we are going to deal with here, that is x to infinity. Here again square root of 2 alpha would appear here, here also we are going to get square root of 2 alpha, and then when we club these two things together, okay, and here you see my negative sign, so plus sign would appear, so that would resemble with exactly the definition of g alpha g, okay, because what we have just divided into parts, we are going to get those two parts, which we can again combine to get minus infinity integration of e to the power of mod of y minus x, okay, gy dy. So that we do. So square root of 2 alpha we get square root of, so is there a typo? Yeah, there is no typo, because g alpha includes also 1 over square root of 2 alpha, okay. So this is also there, so you are going to get 2 times alpha times g alpha of gx, okay. So we have obtained this thing, okay. Till now it is not clear that how these functions are relevant for us. Actually this is obtained for a general g, okay, but we are going to plug in some f, k, etc. at the place of g, okay. So we do that. So put g is equal to f here, okay, and also g is equal to kz, okay, where z is the given function written in terms of conditional expectation. Okay, first line is the line obtained for g is equal to f case. We can get this thing only for those x where x is not a point of discontinuity of f. Okay, so g alpha f double prime of x is equal to minus 2 times of f plus 2 alpha times g alpha f x. For kz, we are going to write down g alpha of kz double prime, so second derivative, is equal to, again for minus 2k times zx, okay, plus 2 alpha was there, 2 alpha times g alpha kz x, okay. Okay, so now we subtract these two lines, okay, here minus becomes plus minus here. So when you subtract, so g alpha of f minus kz, see here I am using the linearity property of g alpha. Why? Because look at the definition, g alpha as a functional of g, it is linear, it is a linear functional of g. So g alpha of f minus kz double prime x is equal to 2 times kz, k times z, correct, kz minus f of x, okay, and then 2 alpha times g alpha of f minus kz x. So we have obtained this equation. This equation looks quite familiar. So let us see how are we going to do this, because second derivative appears here and then f minus kz also appears here. So we are going to take advantage of that. G alpha, this quantity is double derivative appears and it appears here also. Okay, so here this is obtained for all x which are not point of discontinuity of either f or kz. So if we write down this cleanly, then half times g alpha of f minus kz double prime of x is equal to kz minus f of x plus alpha times g alpha of f minus kz of x. Okay, now we would like to relate this equation, okay, with the original equation. Okay, we note that if we can establish that this function, okay, this is function of x, correct, if this function is exactly equals to z, then we are going to get half times double prime of z is equal to alpha times z here and k times z here and minus f. Okay. So if you can prove that this whole thing is z, where z is given by the conditional expectation as in 2, okay, then using that relation we get that half times z double prime is equal to k times z minus f plus alpha z. Okay. So this we can rewrite again by taking z common, k plus alpha times z, so this alpha and this k together minus f, which looks exactly same as the linear ODE what we have started with. Okay, so to prove that the function z what we have started with, the conditional expectation, okay, that is going to solve this equation, the equation what we have proposed, that the linear second order ODE, only if we can prove this much. So this is the gap. So we need to show now that this is indeed true. Okay, so this is the thing. If we can show that this is true, because for g alpha already you have proved that, okay, the relation already you have established here, correct. For g alpha we have already established here. So only thing is that if this is equal to z, then we know that, okay, z is going to satisfy this ODE. So it is sufficient to prove this is equal to z. So now for that we consider this function s to e to the power of minus s to t kw s du. This is just a continuous function of s, okay, and we know we can use the fundamental theorem of calculus, and this function is actually function of bounded variation, so we can do this. So this is differentiable. So e to the power of minus t to t, because I am now using fundamental theorem calculus, so we are writing down that s is equal to t case and s is equal to 0 case, this difference as derivative of this and integration 0 to t. Okay, so why are we doing this? We are just doing this because to obtain a relation which we are going to use in the next slide. So this is saying that t to t is 0. So this e to the power 0 is 1 minus e to the power minus 0 to t kw u du is equal to the derivative of whole thing with respect to s is kws times e to the power of, because kws comes out, okay, kws times e to the power minus s to t kw u du. Okay, so this is the derivative, so integration of that appears. Okay, so this is just application of fundamental theory of calculus. Okay, so that you can do when your function is absolutely continuous function. Here it is actually differentiable function. Okay, now we consider g alpha f minus z. Why do we consider that? Because we indeed want to show g alpha of f minus kz is equal to z. For that, we are considering g alpha of f, okay, bracket close, minus z. That we need to show that g alpha of kz. Okay, if we can show that, then we are done. Correct? So instead of writing g alpha of f minus kz, which turns out to be very complicated, we are writing the g alpha of f minus z, and that we show as g alpha of kz. So g alpha of f minus z appears here, and after several steps, we would at the end show that g alpha of kz. Okay, so now our task is to just obtain that step by step manner. So g alpha of f, okay, here we are using the definition of g alpha of f. Okay, so e to the power of minus alpha t f of w t dt given w0 is equal to x, that is the definition of g alpha of f. Remember? Yes. So this is e to the this g. This is the definition that you just evaluate the function. I mean, you evaluate the Brownian motion. I mean, the function at the Brownian motion, and you take Laplace transformation. Okay, of that. So here we write down therefore e to the minus alpha t f of w t dt minus. So now we are writing the full expression of z here. That is f of wt e to the minus alpha t into e to the power minus 0 to t k w s ds. Okay, this whole thing is a function of t, and then we integrate with respect to t from 0 to infinity. So now this part we take common. We take e to the minus alpha t times f of wt common here. So then I get 1 minus e to the power of minus 0 to t k of w s ds. Okay, the whole thing dt. Now this is the term which appears, we have already obtained 1 minus e to the power of minus 0 to t k w du is integration 0 to t this thing. Okay, so k times e to the power of minus integration of k. Okay, so we are going to write down that this difference is integration of k times e to the minus integration of k. Okay, so and other terms are as it is, e to the minus alpha t f of wt. Okay, so this integration is with respect to the s variable, so I have ds. So actually I have three integrations, 1, 2, 3. Okay, this is with respect to t, this is with respect to s, and this is with respect to u. Okay, so now what we do, we observe a certain type of rearrangement of the integration. Imagine that here we have that s is running from 0 to t and t is running from 0 to infinity. Okay, so that is giving me some triangular region. So if s axis is horizontal, t axis is vertical, so what we are getting is that s is from 0 to t, so that means from here to here, s is from 0 to t and t is running from 0 to infinity. So basically the upper part of this triangle, okay, is the domain on which I am integrating here, st plane. So this whole thing can also be viewed as t is ranging from 0 to s, and s, I mean t is ranging from s to infinity, t is ranging from s to infinity, and s is ranging from 0 to infinity. So this whole triangle can also be written as, so this is the thing I am trying to write down here. So s comma t, this set, this upper triangle is s comma t such that s is between 0 to t and t is positive. This same as t is from s to infinity and s is positive. Okay, s is positive and t is from s to infinity. So we do that. So here this integration, okay, this whole integration, this looks like a repeated integration. So we write down that as, I mean, so here actually I have jumped a step. I mean, this expression should be outside first. Okay, so here this repeated integration I am writing as t from s to infinity and s is from 0 to infinity. However, we would also use Fubini's theorem of f, because we have assumed that that integration of this thing is finite. Okay, so that is nothing but integration. If I write down in terms of if I replace y by wt, and because this is like integration with respect to the Brownian motion expectation, so then we are going to get, this is nothing but saying that integration 0 to infinity of expectation of f of wt, okay, given w0 is equal to x, that is finite. So that is saying that, okay, this function f of wt is L1 function with respect to t and omega together. So we can apply the, so here as you can see that, okay, this thing is same as this thing, correct? So here I have written, so that is going to show me that, okay, this is L1, so we can use Fubini's theorem. So by applying Fubini's theorem, we take expectation inside and this integration outside. So here we have e to the minus alpha t f of wt k of ws, okay, as it is as before. Okay, only thing is that here t is ranging from s to infinity, s is ranging from 0 to infinity. Okay, so here the reason that I want to take expectation inside, because I would like to do further calculation. I would like to use Tower property of expectation in the next slide. So here we, since our t is from s to infinity, we can very well write down t as s plus some non-negative variable. Okay, so we are going to do that. T, we are going to write down t is equal to s plus v. Okay, v is 0 to infinity. Okay, we are also going to use other transformations, okay, one after another. So we first do this thing here, integration 0 to infinity expectation of, so v is from 0 to infinity e to the power of minus alpha s plus v. So where I had e to the minus alpha t, that I am writing as e to the minus alpha times s plus v. Where I had f of wt, I am writing f of w s plus v. Ks, this is as before, so kws is as before. Okay, and here I have s to t, so that we are going to write down as s to s plus v. Okay, kw du. Okay, so this is exactly the earlier integration, just by this small change of variable here. So dt is same as dv, so I can write dv here. Okay, so now here also we are going to change, we will be able to change, because u is running from s to s plus v. So we would write down u is equal to s plus u prime, then u prime would run from 0 to v. Okay, and u we are going to write down as s plus u prime. Okay, good. So nothing else is done here. So e to the minus alpha s is just taken outside of this. Okay, so here we apply Tower property of expectation. Expectation of this is conditional expectation at 0. So we do conditioning at this time s here in between. Okay, so with respect to the filtration till generated by the Brownian motion till time s, and then this kws is measurable with respect to this filtration, so it comes out. We also take e to the power minus alpha s outside this here, and rest is inside. E to the power minus alpha v is here, f of s w s plus v is also here, and this part, as I have already explained, that this is the same thing. Okay, so now here this part we are going to use the Markov property of Brownian motion, that the information of the past and present, conditional expectation given the information past and present is same as the conditional expectation given the present information. Okay, so only at the time s. So here only ws is required. Now since ws is required, so we can imagine that possibly s is the starting point of another Brownian motion. Okay, and so far expectation is concerned, okay, so only distribution law of Brownian motion would be utilized here. So we generate another Brownian motion at time, when ws is there. So from s onward, okay, we call the w prime. So imagine w prime 0 is equal to ws here, and then here everything would be like w of s plus u prime would be w prime of u prime. Okay, w of s plus v would be w prime of v. Okay, so we are going to generate a Brownian motion. Okay, imagining S is the starting point. So it is expectation of 0 to infinity e to the minus alpha v f of w prime v e to the power of minus 0 to v k of w prime u prime du prime, okay, dv. Okay, so this much is okay, but we can recognize this expectation. This is what? This is e to the power minus alpha v. Okay, so this is together, right? E to the alpha minus alpha v and e to the minus this thing is there. So this is precisely the Fein-Markov formula for the solution of the Cauchy problem, what I have stated in the beginning. So this is basically z. Okay, this is basically z, but evaluated at w0 at ws, correct? So evaluated at ws. So this is z of ws. Okay, this is z of ws. Now we have k of ws as before, e to the minus alpha s and z of ws. So k and z multiplication is here, e to the minus alpha s, and integration 0 to infinity is here, and with respect to s the integration is done. So and then expectation is also taken. So this is precisely the definition of g alpha. G alpha is defined exactly this manner here, that expectation of integration of e to the minus alpha t g of wt. Okay, so instead of g here we have obtained kz, k times z evaluated at wt, okay, and e to the minus alpha t dt 0 to infinity. Okay, so this is g alpha of kz x. So this is true, this we have obtained for all x in R. Okay, so here we stop here. So here we have obtained that, okay, this z satisfies this equation, but we have not yet shown that z prime or z double prime, they are piecewise continuous. That we have not yet shown, that we are going to show in the next lecture.